A very good evening to everyone. So, as a part of 99th Distance Learning Outreach Program, our today's topic is uh, how to do forest mapping and monitoring using publicly available cloud platform. The popular ones like available in today's time is Google Earth Engine. So, we'll be basically going through the cloud platform available, and we'll be step by step proceeding with the different data sets available and how we can look at the data sets or analyze them from a forest point of view. So here's a presentation. I'll just go through a few slides. Yeah, so basically this is the outline. So we have few slides based on cloud computing, what are the different advantages, benefits, and what is the need, and what is the speciality of Google Earth Engine as a cloud platform available to undertake our studies. So basically, we all are aware of cloud computing these days, right? In modern world, we all are using networking gadgets, networking websites. We all are using our mobile phones, desktops, thin clients, right? So all the resources, all the applications which we are using, they are basically hosted somewhere on the central, somewhere in a central location, and all the resources are made available to the user through the network. So basically that is the idea. Cloud means a hub where all the resources are hosted. So a broad classification of structures of cloud computing are public, private, and hybrid. So it's not very important right now. So we'll just move forward. So we all are aware of the types of cloud services: infrastructure as a services, platform as a services, and software as a services. So basically we use so many apps these days in our mobile phones. So not only we are using the mobile applications, we are saving our data also. So we are getting the data storage also as a service to a service, and we are also using the application. So that is also a service. So basically this is a major classification of cloud services. So we all know the benefits of cloud computing are that all the resources, as they are not managed at the user level, all the resources are managed at the central level. So it's easier and comparatively better to manage them and to maintain the resources so that there is no malfunction, and the usage and the of overall application and data and network is smooth. So basically, what is the need for cloud computing? Because when we talk about Google Earth Engine, as we can see in this slide, so basically there are three major components. Like we have satellite imagery, we have huge satellite data sets available from a massive historic timeline. So all those satellite images are available on the Google Earth Engine. And not only data sets are available, there are it provides a application programming interface also to the scientific community so that they can use the inbuilt functions or pre-made functions, and you can use them for your study. And we'll just go to the platform and have a live demo, but before that we'll be just going through these slides. So purpose is to give an interactive environment to the user. Once we go to the cloud platform, we'll be able to better visualize and understand what are the components of this cloud platform. Broadly, they have data sets. As you can see, the point number one, there are huge data sets available, computational infrastructure, all the resources, processing power that will be managed at the central level, at the server level. You have APIs there. So basically the API is JavaScript, but if you want, you can use Pythons also. There are additional Python libraries which you can use to integrate Google Earth Engine with your Python environment. Very popularly used these days are like Jupyter notebooks. So if anybody's working with a browser based Jupyter notebook environment or any other R based environment, they can integrate, they can use certain packages to integrate Google Earth Engine. Pretty popular one is Gmap, that is being used by Python, that is being used in the Python environment to integrate with Google Earth Engine and get the access to the satellite imagery and datasets. Then there is also provision you can create geospatially aware apps. It gives you, like through programmatic approach, you can develop different widgets and different interactive components on the Google Earth Engine itself, or you can also create the same on the Jupyter notebook. You can create a UI basically to operate you can create a UI for your own study and display the results. So that comes under the apps part. So I'll just quickly come to this slide, which shows which are the frequently used data sets in the Earth Engine data base available. As you can see on the data sets, Landsat is there, and then data sets are mentioned. Then nominal resolution, temporal resolution is also available for Landsat 8 OLI. If you see, it's 16-day, it shows the temporal resolution. Like every 16 days, there will be an image captured by this OLI sensor for Landsat 8. Similarly for Landsat 7, Landsat 5, and then you can see there is another column which is named as temporal coverage. It shows you like since when the satellite was active in the orbit, and it is now shows presently also it is active. So 2013 to now means this Landsat 8 sensor has been in action since 2013. It was commissioned in 2013 and it is still working. And special coverage, special coverage means it shows you like what is the region, what is the coverage, and which particular country or which particular continent. But if it is mentioned here, it is global. That means it has a full special coverage of full Earth. Then there are other data sets: Sentinel, Moody's. Then there is other imagery is also mentioned there. Then there are digital elevation model data sets also available there. As you can see here in this next slide, topography data, land cover data, weather related data is also hosted there. Yeah, so this is the procedure to access Google Earth Engine code through browser. So if there are people who are currently listening to this lecture, they can also simultaneously undertake the study, or they can follow along. If you have a Google Gmail account, you can just log in into your Gmail account, and after successful login into Google account, you just need to open a browser and type this URL. Sorry, I'll just go back. This URL you can see in red color: https://code.earthengine.google.com/. So if you enter this, first you log in into your Gmail account. After that, you open another tab in your browser. Just enter this thing in your browser, and you'll whatever comes up is Google Earth Engine Cloud Platform. I'll just give 5 seconds to this slide so that people, if anybody's following, they can follow these steps. You can use any browser, Google Chrome or Mozilla Firefox. Yeah, so I'll just give some time. Okay, I'll just move next. Yeah, so we'll go to this Google Earth Engine platform itself, but first I'll just show you a snapshot here. Okay, this is how a typical UI looks like in the Google Earth Engine. I guess it's time. I'll just move to the platform now, and I'll just demonstrate from there. Yeah, so I'll just, so I hope this is visible. So this is my this is the URL: https://code.earthengine.google.com. So once you load this URL, you will get this screen. So as you all can see, there are basically 4 major components here. First one is at the bottom. This one is an interactive map, right? So whatever if you want to search something, you can search here. Like if I search a place, this is a search bar. If I search Dehradun, this interactive map will show me the geography. I just search for Dehradun, right? You can see, if I zoom in, you can see this Dehradun. Then there are certain interactive components available on this map component here. On the top right, you can see this map and satellite map terrain. You can select. It will change into a terrain visualization. If I select satellite, so it will show you the satellite view of your place, right? So this is basically an interactive map here. You can use you can create ROIs using this, like here, and it will display here. So the very important component of this screen. First one is interactive map here at the bottom. Then we will go towards the top left side. Here we have three tabs: scripts, docs, assets. Scripts means, but first we'll have a look at assets. So here there's a provision new. If you want to do certain study, if you have your own shape file with you or KML file, or if you have any satellite imagery with you, you can upload here directly. If you click on new, it will show you options. GeoTIFF files, if you want to upload certain files, you can upload here, like source files, upload a new image asset, and you want to work with your satellite imagery which you have, you can upload it into this platform and you can continue working on that, right? So this is for that. After that, you can also upload shape files from here. If you click this, it will show you. You can provide an asset name here, test shape file or something. You can give an asset name. You can select files from here. So basically, when you choose a shape file, it will show you a message that you have to select the .dbx file and other necessary files required with the .shp file, so that it can work perfectly for you. So basically, this assets tab is assets, whatever you are maintaining as a user, whether it's your satellite images, TIFF files, or shape files or CSV files. So you can see here I have a list of shape files here. Maybe we'll be using few of them for our study here. So you can go to docs. Docs means basically what are the docs already inbuilt functions. Like a very popular one is map. So basically this map will help us, this map documents functions will help us plot our maps on this interactive component here for better visualizations. So these were the APIs or functions available by Google Earth Engine which we can use. Okay, so now we'll have a look at scripts. So these are our scripts. What you can see an example script here, the name is LULC classification 2021. So basically this is land use land cover classification done in a certain region. This was done in Uzbekistan, Birchmiller Forest Basin. So this study was done there. So basically this is the entire code we have written here. So this component, this is a middle component, right? So you can see I can just cover this, it will highlight and show you. Yeah, so this is the middle component, and here where you exactly put your JavaScript code to manipulate your data sets, right? So if you write certain script here and you want to save it, like you can click here, save as, save with description. So you can save these scripts, all these scripts will be available here. So that is the idea. And on the top right, we have this console where if you print anything, it will display all the printed articles here. Okay. So what we'll do now, we'll take an empty script and we'll just pull certain data and just see how it works, how we can get familiarized with this Google Earth Engine. So just open certain demo. Let me open this. So this is a pre-saved script. So what I'll do is I'll just yeah. So there's a search bar provided at the top, right? I'll just remove this code. We don't need it right now here. And these data sets also I'll remove. Yeah. So I'll just search here. Not only places, if you search like Sentinel-2, if you search, you'll get rasters. Rasters means these are the data sets. Then here is very light color. You can see tables written. So basically that is related with vector formats. So here is places, but there is no place with Sentinel-2. So it shows you rasters. So So these are the data sets available. So you can see Sentinel-2 multispectral instrument, level 2A data. Then there is level 1 Sentinel-2 MSI multispectral instrument, level 1C data. So level 2 is more processed, atmospherically corrected. So if you want to see the properties of this data set, just click this, right? There is a symbol here, import. If you click this, it will directly be imported into your script. But before importing, we just want to check. So I'll just click this. So you get a new window, new pop-up. If you, right, you can see Sentinel-2 MSI multispectral instrument level 2A. You have this picture prototype here. Then you have data set availability. So this level 2 data set is available from 28 March 2017 onwards till date. Okay, data set provider is European Union. Then this is the collection snippet, like program. This is, you are invoking this data set, importing into your editor, code editor here. Here, I'll just see. So if you click on run, so but this, whatever script you write, it will just run. So when it runs, you can see console enlightens with the orange color. You can click this and you can see it prints here. Yeah, so whatever you want to display or you want to see a data set, you can just print it. It will display here and you can just go through it. So I'll just go to Sentinel-2 dataset again. I'll click this. So here there are different bands available, different categories. If you click on description, you will see description here, right? So you can read about this data set here under the description tab. If you go to bands, you get a table here. So you see the name of the bands, then there is another column with description which shows you what is the description of the band. Like B1 is aerosols, B2 is blue band, B3 is green band, and so on. So you get to see the description. And there are min max resolution of each band, this one. So you can see B1 is in 60 meters resolution, B2, B3, B4 are in 10 meters resolution. Likewise, there are resolutions mentioned for all the bands, right? And then there is wavelengths mentioned also. Okay. Then there is something called image properties. So these are the image properties. Then cloudy pixel percentage. Image properties are the metadata of the images. Like if you want to visualize certain images that has a particular cloud content, like if you want to visualize certain images with 50%, 20% image, then you can filter your dataset using these properties. Okay, so I'll just close this. There's another tab, terms of use. You can close this, or you can click on import. The moment you click on import, it will be imported, right? See, you can see this. Yeah. So in the middle component, which is the editor where you use JavaScript, you can see there is this fine line where you can see all your imports, right? Imports, one entry, import generated code. So this is this snippet. So here is this variable image collection, Sentinel-2. So with this data set, you have imported all the images for Sentinel-2 captured ever throughout the full global extent, that is the full Earth. But you might not be interested in the entire Earth, right? So you might be interested in your region. It could be anywhere. You probably could be interested in a certain study in your region. So what I'll do is I'll just try to import a shape file, right? But before that, you just do one thing. There will be a variable created with image collection. So I'll just rename this image collection as S2. So by S2, I can remind myself that it is a Sentinel-2 image collection. So now on, in my entire JavaScript here, I'll be referring to this data set as S2. Okay. So first, this is first step, which is called importing a dataset. So now you are aware how to import a dataset. So this is one way. The other way of importing a dataset is programmatically. So I'll click on the dataset. You can copy this collection snippet from here, right? It shows it is copied. Now close this. I'll create a variable s2, and I'll just do control V and copy this. So this thing here variable s2 is, and this thing here variable s2, both are the same thing. So if you try to run this, it will throw you an error. Probably not right now, because usually if you want to refer, once you start referring, then it will be an issue, because there are two variables with same name. Okay, for now I think it's doing fine. Yeah, so first we'll see how to import the dataset. See, in case I delete this, I have no problem, because I have already imported it using the programmatic approach. Every dataset collection will have a unique name, unique ID. So this is Copernicus Sentinel-2 surface reflectance product. Image collection is a function which holds a collection of images, that is the dataset. So this is how programmatically you can import. So just now we saw there are two methods of importing. One is programmatic and another is through this UI search. You can just directly import this, so it directly comes here. Yeah. So if you don't want to use this, the advantage of using a UI based importing datasets is that you can just click and you can always go through the bands or any information you want related to the dataset. So I prefer using this importing through UI. So I'll just name this as S2, and either it's up to you. You can comment this. Comment means this particular line of code will not execute, or you can delete this. For time being, I'll just maybe remove this. Okay. So this is first step, that is called importing a dataset. Now you have the dataset. So let's either, but you want to, now the second step is filtering the dataset. So filtering is, how do you filter the dataset? So your study may be dependent on a particular time domain, like 2020 to 2021, or 2015 to 2020, or maybe it is a decadal study, right? So you can maybe you are interested in a decadal study 2010 to 2020, right? So you can filter the dataset based on what is the time domain you are looking for. Okay, so I'll just demonstrate you how to filter. We'll just write here filter. I'll create a new variable s2 filtered, and now as I'm going to create a new variable, I will use the variable created earlier which stores my entire data set, right? So this is the data set from 2017 28 March onwards, and its special coverage is entire earth. So I'll just filter it as to dot. Once you do dot control space, you'll get the entire list of functions provided by the class image collection, right? So I'll just do FIL. If you type filter, you can see here filter metadata, filter date. So not only the function is there, but on here you can see it also displays the definition of the function, right? Here it shows you the definition of the function. So control space, so you can see the definition. So what it will do, I'll just click this filter date and I'll just pass two parameters to filter the date, to filter between these two dates the entire images. Okay, so let's suppose this is 2022. Suppose I want to check for from Jan 2022 to January, February, March, April, May, right? So this is YYY, MMM, and DD. That is the format, right? So it will pick all the images from January to May 2022. So This is how you have filtered it. I'll just run it, but you won't get anything because it has done the job, but you don't know whether it has already filtered. So you need to print your variable and check. So I will print this variable s2 underscore filtered. So I'll just s2 filtered. I'll just try to print this. Okay, let's try to give a run and see what happens. So here you can see in the console, image collection, it is running. Yeah, so it says that image collection error, query aborted after accumulating over 5,000 elements. So there are huge number of images here. Shouldn't be the case though. I'll just let me just try to print the size. If you print s2 underscore filtered, it will try to print the entire image collection, so which is a very heavy task on the server. That's why it throws an error. So you have to be very efficient when you are writing your code. You have to, it should be pretty optimized. So I'll just type dot size. Still it's taking so much time, and it is trying to get the number of, yeah, so this is the number of images, which is pretty huge. That's because we have just filtered based on the date. So we will apply some more filtering. There are basically broadly three basic types of filtering. So that one is based on the dates, filter dates. Another is, and now we are doing something called chaining of functions, right? So either I can create one more variable and I can name is s2 underscore filtered to filtered. I'll do chaining means I'll directly call another filter here. Yeah, so I'll do filter bounds. So when you do filter bounds, you give a geometry like onto which you want your images to be, you know, which is the region you want your satellite your data set to contain, so that your study is relevant and fruitful. So I'm just trying to see if I have a shapefile here, or we don't need a shapefile also. Like I'll just switch to satellite mode. I'll just create a UI. Either you can draw a rectangle in this interactive module here. You can use a rectangle, or you can use a polygon or a line shape or a point, geopoint. So I'll just create a rectangle here. Okay. So let's suppose, sorry, I'll exit this. Somewhere, anywhere you can create this. Maybe somewhere you can see a little forest also. Suppose I'm doing it over Chandrabani area here. I'll create, okay, it's already created. I'll just delete this. So basically you are creating this UI to understand that how you can filter your huge data set based on the dates first, then based on this ROI. So the moment you finish creating this rectangle, you can see there is a variable geometry displaying here, the same rectangle here, right? So I'll just rename this. You can rename it to anything, or you need not even rename it. You can use it as with the name geometry. I'll just do ROI. Okay. So with this name, with this ROI variable, I can filter again with S2, which was the earlier data set here, which is the biggest one. So I'll just filter date to 5 months. Okay. Just do this 31st. Let's see, 31st May. 1st Jan to 31st May. Then filter bounds ROI. Then again we'll see how much is the size. So this was the size printed before you filtered it with the region. See, now you got only 56 images. Why? Because there are only 56 images that are covering this particular region. So that is how you filter your data set. Okay, now I'll show you one more. There is something called filter metadata. So here you have to pass the metadata properties, and you can pass something like less than comma maybe 10% or something, right? So this, from where I'm getting this is basically, if you check your data set bands image properties, so you will see here cloudy pixel percentage. So depending on your study, depending on your requirement, you can use any of these properties and try to filter your data set. Okay, so less than 10. So I'll try to so this is called chaining. So this is the third filtering type we are doing, right? So the first one was filtering by date, then filtering by filter bounds using filtering on your region geometry. Then we are doing filtering with metadata, that is cloudy pixel percentage. So I'll just try to print and check whether it has already filtered or not. So the very important thing is, S2, we have applied these functions filter date, filter bounds, and filter metadata on S2 itself. Okay, so I'll just try to print this. So see, earlier it was showing 56 images, but now as you filtered with this cloudy pixel percentage metadata property also, so it shows you only images that have cloud pixel percentage less than 10. So it shows you 33. If you increase this further, let's suppose I want to include images with 20% cloud cover, I'll just run this. So it shows you 40. So I hope you got the idea. So this is the basic idea. First is importing the data sets. Second is, just a moment. So first is importing the data set, then is filtering. Okay. The third is mapping, which is the major task here. So we'll just go and we will just check how to map. Okay. So we will stick with 10% and we'll just run this. So now we have a data set S2 filtered, which has images from 2022 to 2022 May, Jan to May, based on this ROI, which we created here near Chandravari in Dehradun. And we left. So basically, after importing the data set, we have done the second step also, that is filtering your data set based on three major criteria of filtering. That is, one is based on time domain of your study, another is your region of study, another is what are the metadata properties you are interested into, if that affects your data set on your region of interest. So after this, now we will see the final data set which we have has 33 images, right? So how did we got this info? By printing. So that is the use of print command. You can just try to print anything. In case of s2 filter.size, if you print s2 filtered itself, it will not print the size, it will print the entire image collection, right? And you can see it shows you the name Copernicus S2SR 33 elements, that is the number of images in this entire collection. Version, bands, features. So there are these 33 images you can see. This, yeah. So each image has a unique name, this ID, unique ID. So you can even if you are interested only in certain images out of these 33 images, you can invoke these images one by one using this ID field, right? Then these are the properties. These are the properties of the data set, this entire image collection. But if you go to the features and image, you'll again have properties. So those are basically metadata properties. These are the properties of this particular image. So every image will have these properties tab and bands. These are the bands which we checked in the data set also. So every image is having these bands, 22 bands. All right. So this print command gave you an insight into your image collection, which you have after filtering, right? So we'll proceed further. The next third major step is adding your images to the map, right? So we will use something called map. Here you can see, right? If you type capital MAP, you can see the color changed also to violet. If you type small map, nothing happens. That means it's not a keyword, it's not a function in Google Earth Engine. So do capital MAP dot, you do control space, you get so many functions. Function means a task, so you can assign a task to map and then it will deliver that task here in this interactive map. So what we'll do, let's try to map the first image of this image collection. Okay, how do you get the first image? So I'll create a new variable first image. So I need to call this variable s2 filtered. I'll put it here, dot control space, sorry, you just type first. So the color changes, so that means it is a keyword. You put bracket parenthesis here, bracket. So you don't need to by heart these functions, just do control, just put a full stop, then put a dot, type first few words of the function, control space, it will automatically display you the functions. So you can use this first. So what this will do, S2 filtered is an image collection of 33 images, right? You can see here 33. So out of the 33, it will give you the first image. The first image is, it will be a single image. So I'll use something called add layer. There's a function called add layer, right? So this add layer expects inputs. I'll just pass first image here. Let's see what happens. So I'm adding to this function, I'm passing this layer, first layer, that is dot first. I've created a new variable. So this new variable here, this first image means it is the first image of this filtered collection. So let's just see what happens. I'll just click on run. So you can see here something coming up, layer 1. Yeah, so this is the first image coming up, but you can see it's too huge, right? Our study region is very small, but the image is very big. Probably this is the size of the image, but somewhere here if you focus you can see your ROI. So it's not that appealing visually. So what you do, there is something called clip. You can clip is a function used to clip the satellite image you are interested in onto your region of study. So you do first image dot cl control space, you'll get another function called clip here, clip geometry. So what is the geometry you want to clip onto is your ROI, right? So now if you run this, it will not map entire satellite image, but it will only map onto your ROI. Yeah, so this is very small, but you can see, we'll just zoom in, right? So from here you can unmark this ROI. You can unmark this ROI. Okay, so now you have this black patch here. So this is your satellite scene, right? But as you can see, you have mapped the first image to the map, but you cannot visualize anything, right? So for that, what you can do, you can either go here, layers. There is certain settings configuration button here. You click this, right? So you just check. Okay, so these are RGB channels here, right? So whatever image you have right now has multiple bands, because this is a multispectral instrument. So it is not a single band image, there are multiple bands. So if you want, you can use these channels for visualization, better visualization. So maybe we can do RGB. So before going into that, I'll just stretch the values. You just give a stretch factor of 98 or 90%. Before going into, we'll just see what we can see. Yeah, so you just gave a stretching to the values, and it helps you in a better visualization of the image here. So here is the urban area. You can see the vegetation, you can see the, right? So this is how you add an image to the map, right? So yeah, so now we talk about what are different things we can do. You can map the first image. Now if you want, you can give a particular name also to this image. Let's type the name as first image. What I've done is, here earlier we had this thing. I'll just put it here and comment it. Okay, so if you do this, you have only given to add layer function one image and clipped it. So that is one parameter. But now you are passing multiple parameters. This is layer which you want to map, which you want to add to this map. Then these are visualization parameters that decides what are the bands you want to visualize in RGB channels. Okay, so you can specify each band. Then third, like comma separated variables are parameters are there. So third one is first image. So if you run this now, you will get the same image, but you, instead of layer one, earlier you were getting default text here, layer one. Now you have first image, right? So you click this, you can if you unclick this, you'll, the image will be removed. If you click this, you get this image. So let's do one thing here. As it is a multi-spectral image, it has a number of bands. Let's try to visualize something called true color composite and false color composite out of this image. So this study, this way we can learn. I'll just pass. The band names are SRB4 and SRB3, SRB2, right? So bands means you have passed the bands. These, first one is red channel, second one is green channel, third one is blue channel, RGB channel for visualization for human eyes. Okay, so it's up to me what are the bands I want to put into red channel, green channel and blue channel. I'll just confirm again. I'll look at the data set and then check which are the bands. Okay, so we have given, so there is no SR actually, right? So you can use these names also for bands. So B4 is red. In red channel we'll put red, in green we'll put green, in blue we'll put blue, right? Sorry, B4, B3, B2. I'll just close this. Let's try to run this. We are hoping to get a true color composite visualization out of this. True color composite. So it's pretty obvious why we are referring it as true color, right? Because in red channel we have put the red band, in green channel we have put the green band, and blue one blue. So whatever is red will show red, whatever is green will show green, whatever is blue will be shown as blue. So automatically it becomes a true color composite. So let's run this. I hope it gives an error. Yes, so there is an error here. Why? What is the error? So once you become good at reading the error, you will be able to resolve the errors too. Okay, there's some issue. So image or no band named SRB4, obviously. So the band names which we have given, they are not correct. We just refer to the dataset also, right? So there were band names were, you can refer to this. B4, B1, B2, B3, these are the band names, right? There is another dataset which has naming as SRB1, but not this one. So now this will run. So I'll just run this and we'll see. Yes, it is running now, no errors. Okay. So you have given bands for visualization, but still you have not given any min or max value. So it's showing as black. So we'll just fix this from this configuration here, custom. We'll just stretch the values if you want 98%. See, you can see here, 3 bands RGB, B4, B3, B2, right? I'll just apply because you have already given them by default. Yes. So now you got this image, which pretty much looks like the background, right? So it's kind of gives you an insight or idea like, okay, this is a true color composites. So the vegetation area shows in green, and all the urban settlements you get to see like in little bluish, whitish, but all the major green things will be showing in green, right? So this image, this is how you can map a true color composite for any image. But for demonstrating purpose, I just imported a Sentinel-2 dataset. I filtered it. That is the second step. Filtered it using dates, my region of study, metadata. I filtered it, right? Then I pulled the first image out of this collection. then I'm using that image here. I'm passing the bands, right? And I passed a name to this map add layer function. So it added this image here. So this is our true color composites. There's a button here. You can go to full screen also. So you can see this. It's pretty hazy because of this, but right. So now let's try to so this is called true color composite. Same way we can have a false color composite also. I'll just write it false color. So it's pretty obvious whatever is not true color is a false color, right? So but what we will be talking about is standard false color composite. So how does it become standard? You have to just change these bands here. So it will become red, it will green, and in place of red we pass NIR. B5, B4 with NIR, red, green, right? So this particular combination is called standard false color composite. I'll just cross verify. So this is why I said if you import the dataset through UI, it's a sophistication for you. Like you can refer to the datasets or anything. Okay, this is not B5. So NIR is B8, right? So you have to pass there B8. So this is so now I'll just I should have written it as TCC image, right? True color composite. This is standard FCC, or you can write FCC. Standard FCC. I'll just run this and we'll just try to visualize them. So basically this is the first image, but I've tried to create a standard FCC and one true color composite of that image. So true TCC we have already seen. I'll just unmark this and we will see the SFCC image. I'll just click here and I'll just give a stretch value, maybe 90% or 98%. Let's apply this. Yes. So you can see this is the FCC image. So you can see all the major green areas are showing in red. That is because vegetation has higher reflectance in NIR region, but we have put NIR band in red channel, right? So whatever reflects more in NIR will show red. So that is the vegetation. It's pretty simple. So whenever you are trying to visualize, it's up to you what are the bands you are putting in red channel, green channel, blue channel. If you put red, green, blue bands in all three channels, it will be TCC. Any other bands if you put, it will become automatically non-true color composite, that is false color composite. But out of that also, this particular combination is a standard FCC. Okay. So that's a first step. How do you handle the datasets? You import the datasets, you filter them, you pull out the image, you map them. You can map true color composite FCC. Now we will just have another example. We'll just try to calculate NDVI for this image, right? So I hope you all are aware of NDVI. That's normalized difference vegetation index. So yeah, so this is our image, right? So I'll just pull this. I'll create a variable NDVI. Let's see how we calculate that. First image, there is an inbuilt function already given, dot control space by the image. Something is wrong. What is the issue? Control space. This is filter dot first image. Yeah, it's like you have to type something. So if I type normalize difference, yes, so it has come. So once you put the dot, you just type whatever the function you're looking for. Suppose I cannot recall, but I know it starts with N or. Then I do control space. It will list all the functions starting with NOR. But I think here only function available is normalized difference. So normalized difference function takes two input. So any two bands if you pass to this function, it will calculate band A minus band B divided by band A plus band B kind of calculation. It will do that and it will store into this, right? So NDVI is NIR minus red band divided by NIR plus red band. So I'll do that, but I cannot write NIR here, right? Because NIR is not a band. So what is NIR band? It is B8. So I'll pass B8 and I'll pass B4, right? So I run this. So okay, there is an error here. If the bands to use are not specified, use the first two bands. If not the first, there's some issue with the way we have passed the parameters, I think. Let me see if this is the issue. Yeah, this was the issue. So it's basically you have to pass a list of bands. So once if you pass it like this, it's not taking it. It's so you have to. This is a data type popular in Python also and JavaScript also. You have to create a list. You do these brackets and you can pass list of bands like B1 comma B2. Sorry, here you can pass n number of bands, right? B8, B3, B4, B3, right? So let's suppose I create this as variable list, right? List. And if I pass this list here, it will do normalize index for all these three bands, or it will do something. Or let's see what it does. Yeah. So I think now it's trying to do B8 minus B4 minus B3 divided by B8 plus B4 plus B3, but that's not what we are interested in. So I'll just remove this. I'll pass this list here. Okay, so now it will be B8 minus B4 NIR minus red upon NIR plus red. Okay, so I'm interested in checking what this variable type is. What is it? Whether it's an image or what is it? So I'll print this so that I can get it here. You can, in case you are doing actual coding or actual study, you can pass characters alongside printing so that you know which yeah, here we can see NDVI written. So I know, okay, the variable which I printed here, I can visualize it here. I'll just click. This is an image. So that was the purpose. I just tried to print this. So when you do any operation on any image, basically it will result into a new image. So list one, there is a band called NDVI band. So that is by default it has given. So what it has done is from the first image, it used this function and you have passed a list of NIR and red. So using NIR and red, it has calculated NIR minus red upon NIR plus red. That is the basically NDVI value. And as you have not given any rename function to rename the band, by default it has given a name called ND, right? So we can rename it also if you want. Control space. Let's try if we can do that. So what I'll do, I'll type it as NDVI. Okay. So now you are not only calculating the NDVI of this first image, but the band name also you are giving NDVI. So let's try to run this again and see what happens. It is again printing this image and we can see, yes, you can see here the name is NDVI, right? Okay, so that being done, we will add this image also along with our TCC, FCC, and DVI image also. We'll plot it. So anytime you want to add a layer, you have to use map.add layer. So I'll just put NDVI. Okay, NDVI, and again I'll do the clip for this image also. Visualization parameters. Okay, not required. Let's put it. In case you don't want to pass any visualization parameters, you just pass this parenthesis and leave it empty. Okay, it will work like this. So you just type it here NDVI. Okay, so you run it. I just run it. Okay, there is an error. So you also learn how to read the map.add layer is not a function. So it says add layer is not a function. Obviously add layer is not a function. That is a miss. That is a typo happened here. So now it's fine. So it's very important to go through the error, you know, and understand it and just correct your code and run it again. Okay, so now it's working. Yeah, see, you got this. So you can see the first you printed TCC image, then you printed SFC, then is NDVI image on the top of it, right? You can see it. I'll just maximize it. Yeah, this is the NDVI image. There is on the top right, there is something, a tool called inspector, where you can see each and every pixel value. I'll just click somewhere and it will show you. So pixels means whenever you click a pixel, all the images which you have mapped to the map will display their values. So we are not interested into SFC TCC right now. I'll just go to NDVI. I'm interested in the values of the NDVI images, because if you remove this, if you do this, base map is there right here, Chandrapani. So you can see which area is vegetation. Okay, so vegetation area is little grayish whitish in color. I'll just click this, and here you can see on the top pixel it is loading the values. It's 0.388, right? I'll click somewhere else also. 0.38. Now I'll try to click on the darker regions. Maybe here, let's try 0.18. 0.18. So I'll just click on a darker area here also. There 0.08. So you can understand, as this NDVI image has a single band, so it is a range of values, right? From dark to gray. You can even add visualization colors to this, because right now it's like gray scale. It's from 0 to this thing. It is showing you, so all the lighter color regions which are showing higher NDVI values, obviously we know, looking at the base map also, that they are vegetative areas, right? So the vegetation is showing higher NDVI values, which is obvious, and all the settlements, you won't be having a very good, you'll be having darker areas in the settlements, right? That shows that the NDVI values are not very appealing. So NDVI is just one index. You can use multiple indexes. Okay, so this is the basic setup, how you go about importing data sets and how you go about filtering the data sets and mapping. So this particular basic module helps you with importing data sets, filtering, and adding the images to the map. So now what we'll do, as we have learned what is TCC, FCC, and how to calculate NDVI or different indexes, we will try to go and classify a particular region, right? How do you classify into different land use, land cover? And then once classification is done, we can see how much we have mapped under forest, how much we have mapped under urban settlements, how much we have mapped under agriculture, like that. And then you can also calculate the area for all of the land use, land cover patterns. For that, we can use something called supervised classification. I'll shift to another script for that. And this is whatever we did here in this script. It was using Sentinel-2 data, but for supervised classification, I have another study region that is from Uzbekistan that was done in one of the recent projects in the department. So I'll just go to that site, and we'll be working with Landsat data there. So it's good to have a different blend of data sets when you're working. Okay, so I hope we are through with this module, and we have learned like how to actually do a certain analysis on the imagery. Here to map.add layer, I'll just remove this. To map, you can also maybe provide, so as NDVI is single band image, when it is a multi-band image, you can pass bands as a visualization parameters. But if it is a single band image, you cannot provide bands, because you don't have a list of bands. There is only one band, so you have to provide something called palette. Not sure, just check the spelling. Okay, let's try to give a range of colors to the values of NDVI so that we have an idea. So we'll start with what? Dark brown, brown to yellow to green. We know green color will be the high NDVI values, right? I'm not sure what's wrong. Just a minute. Dark brown. Okay, this is the issue. Yellow, green. Fine, you have provided a list of colors. So dark brown will be the lowest values from lowest to highest. This is the color gradation. So if the color gradation should be very important, like it will indicate the values. It will give the idea in this sense of the color. So I'll just run this, and we'll just again have a look at the NDVI.slip, NDVI image which we plotted. Image visualization error is there. Color is not a valid CSS 3.0 color. Okay, so there is some error with the kind of color you have given. So you don't give dark brown, you give maybe this. Let's try this. Yeah, again, color is not in, so I'll just give black, black, yellow, green. Yeah, now it's fine. Yes. So you can see the values here. This is how you visualize your image. So probably there are the regions with green have higher NDVI values. You have you have given a palette. Regions with yellow are the regions where their NDVI values are lesser than the regions depicted in green color. You can visualize and just click and check NDVI image, and I'll just click on a yellow image. 0.098. See, so hardly there is any black regions either. I don't think there is. If you cannot visualize properly in black, that means maybe there's no region as zero or something with NDVI values zero or like that. You can remove this also if you want. Let's see what happens with this. So what I'm trying to do here is I'm trying to split a single band image into range of colors so that it gives a meaning to me when I add it to a map, and it helps me visualize it. Yeah, yellow to green. So you can see these dark patches, green patches and yellow. Or probably you can have a black. It helps visualize better. So this is about importing data sets, filtering them, and adding to the map, visualizing true color composites, false color composite, calculating indexes, which are very important. Indexes are basically a sense or idea of certain output you calculate using the spectral bands, right? So this was using Sentinel-2 dataset. Now we will move on to Landsat, and we will just see how we are doing a land use land cover classification, how we are mapping the forest, and how we are calculating the areas, right? Then towards the end we will also have a monitoring time lapse video which is available in the Google Earth. So for you can also check out this developers google.com. All the help code, all the datasets information is available here, and it's in public domain. You can just go to this site and you can just see datasets available, compute APIs, everything is available here. Datasets, if you click, you can go through planetary scale platform for earth science data analysis, climate and weather data. You can go through this variety of datasets hosted here. Surface temperature products are also there. Climatic data is there, atmospheric data, weather data, imagery, Landsat, Sentinel. If you go to Sentinel, you click on Sentinel, it will further give you a categorical chart. Yes, Sentinel ones, that is microwave data set. Sentinel-2, that is optical data set. So whatever study we just did, we did with the optical data set. See Sentinel-3, Sentinel derived data sets, Sentinel-5. So basically this is where you can go for any help. If you go to click on Landsat, it will not only give you Landsat tier 1, tier 2 data is there. Tier 1 is the most premium quality data. So I'll just Landsat 8. If you go, it will not only it will give you information about this data set, it will also give you the code provided, and you can directly copy it and put it into your GE editor, or you can directly click on this and it will open in code editor. It will automatically by itself open this code, and you just have to click and run. So it will run and give you the visualization of this data set, right? See, it's taking some time here to load. See, it's automatically loaded here. So that's why it's very helpful. You can always go to this Earth Engine data catalog for any help. So now let me go to I'll just close this and leave page. I'll just close this and I'll open up this again. Google Earth Engine code you have to type. Yeah. Okay. Just trying to get the heck of. Yeah, I'll just open this LULC classification 2021, Uzbekistan. I'll just go to Uzbekistan district where we use. So this was the region. Yeah, so this is the region. Okay, so this is the shapefile we have hosted already in my account. You can see users Ashish Bisht, Birchmiller Forest. So this is Birchmiller Forest. You can see this is the file. If you click this, it will show you asset details, description, features, properties, right? This is the shapefile. You can see this. This is the shapefile here. You close this and you can import it using this button here. You can rename it if you want. You can share this with somebody. You share your code. You can share get link. If you do get link, you can send this link to anybody so they can access the same script, but there will be resources which you might have used like shapefiles or uploaded TIFF files in your script. So in case you want them to access those resources, you have to give permission here, share. So it will open and you have to add here, right? You have to add their Gmail and give access. So that's how it is done. So if you click on this, it will import it. I'll just click it. Although I have already imported it and renamed it to region, I'll again just demonstrate how to import this. See, it comes here as by default table. So I renamed it to region. So I'll just remove this. So I'm using this region. So we'll proceed. So this is Landsat LC08 collection 2 tier 1 data. Okay. So this is a apply scaling factors functions, which is also given in Google's website. So by default, you can copy from there. It's related to the pixel values. So you have to multiply and add an offset of minus 0.2 to all the bands, surface reflectance bands. So basically this Landsat 8 is going to have surface reflectance and surface temperature products. So we are not interested right now in surface temperature here. We are doing land use land cover classification. So we'll be doing using surface reflection products. Okay. Yeah. So what we have done here is I'll just show you the training data. How do we acquire the training data? So for the sake of convenience, usually it's not a good practice to put your entire code in one script here, right? Because so what we have done is there's a mechanism provided. We are invoking the data sets from another script named as Uzbek training data. You can create a you can use require keyword and mention the address of this another file. I'll just open this Uzbek training data. I'll open it in another link so that it is convenient to visualize. So basically we have training data in one script and we are invoking the training data into another for the classification. So this is the Uzbek training data. I'll just click this script here. So it will load and show us the training data points which we have obtained, because in supervised classification and unsupervised classification the major deviation is difference is that we create a machine learning what do we call it, classifier or model. We train it using a certain training data. It's taking a little time. And then we divide the training data into validation data and training data. So we divide in a proportion of 80-20 or 70-30, depends on you, whatever is suitable for your study. And you use the 80% of data for training your machine learning algorithm, which helps the training helps it classify your region. And then you can use your validation data to, again classify it and get the error matrix. That validation data will be classified by the machine learning algorithm again, and you can see with how much accuracy it is classifying your validation data. Based on that, you get an idea or sense what is the accuracy of your classification. So broadly, that is, so it's little huge, the data. So it is, you can see variable forest feature collections, all these points will be loaded here. So just stay with it for 2 minutes. So all our training data points were collected here. See, they are loading. Go to Uzbek. I'll go to my study region. Pretty slow. Okay. Meanwhile, it loads. I'll just show you. This is the programmatic way how I have imported the data set, right? Map.set option, satellite will it will help you in the sense you don't have to click on satellite every time you load it. By default, it will be in satellite mode, so it's also helpful. There's applying scale factors for all SR bands, right? Then there is mask clouds functions. So there is a band called QA pixel band. You can select it, and you can mask cloud. You can mask cloud shadows. What mask means basically is you want to hide certain pixels which you don't want to, which are not necessary for your analysis in a region. So you can try to mask them for any reason. Clouds, cloud shadows, snow, water. So we have used these masks here. Okay. These functions are also available in the Google, so you can just implement them. They are also part of, you can say, filtering or pre-processing kind of thing. It's not pre-processing, but it's part of, you can say, effective filtering of your data set. So then there is a band called Q aerosol. So you can also, like, if you want, you can mask the aerosols present in the images if you suspect. Okay, so another important part is now you create indices. You do calculation of indices. So a machine learning algorithm is where you pass to the algorithm all the surface reflected bands, in which bands you want the model to predict, right? So whenever you supply training data, so all those geo points which in this collection of training points can be done in two ways. Either you go to the ground, you take the ground truth, you take the GPS with you and you collect the ground data from there, or you can do is you can use the interactive feature of this Google Earth engine. You can select these points and you can, like, so for example, just show you, for example, I'll just click this. It will show you a geometry. So you go to this, you give it a, you change here as a feature collection, right? Add a property, give it a property of LC, which means land cover, or you write land cover, or you write anything. Just assign it a value 0. Yeah, right. So you have created a class land cover or LC with value 0. Now, in the same class LC, you keep on adding other variables like forest, urban, rivers, or agriculture, barren, and whatever is. So that's how you collect training data using Google Earth Engine itself. Okay. Here we will not be. This is one simple demonstration of how to collect data, how to create training data using Google Earth Engine. But I have already created data, Google this training data in using GEE. So I'll just directly invoke this. It's taking pretty long to load. So I'll just invoke it here. Okay. Yeah. So our training set will be here. As training set, if this file loads, then only I can show you that I have created a function there called training data. So once I load this Uzbek training data script, I get this variable training set, and from this variable, from this script, I extract this function which gives me all my training points for all the classes: forest, urban, agriculture, barren. Okay. So I got it here in classes. Okay. Now what I do, this is taking pretty long. So assuming that I got it here, my training data set, I'll move forward. Okay. Now I have a function. I have created a big function, like a major function, and I'm passing it. I want to apply this function onto my entire image collection, entire Landsat data set. What I want to do is, for all the images, I want to calculate NDVI, right? NDBI, normalized different built-up index, soil assessment savvy index, elevation slope. So these are the extra, I am creating extra information and adding them as bands in my images, right? You can see here, whatever image you pass to this function, eventually you calculate all these indexes, right? You see, this function is familiar. We just use this normalized difference and then rename this to NDVI, similarly NDBI. And there is a new function called expression, which you also can be used to calculate NDVI. You can pass the expression which you want, whatever formation you want to use the bands to calculate the effective value, and then pass the names. You can name them here, expression, and then to each name you can give which band is assigned. So that also is another method of calculating indexes. We pass the digital elevation model, right? We rename it elevation. So basically these are the, in all the images we already have surface reflectance value, but we are adding these indexes also, so that the machine learning algorithms, becomes even more efficient at classifying. Because for example, it can use slope to distinguish between different land use covers like agriculture, and or urban settlements or forests. So agriculture tends to have a particular slope. So using this slope information added into the image, the classifier will be enabled or made more efficient to classify. So this is our Landsat SR surface reflectance product. So again, we are doing the familiar steps here. We are filtering the data sets, right? We are using cloud cover because if we check our data set, the metadata property name is cloud cover. And here we check for 2021 May to September data set. Why we chose this window? Because there was snowfall after September and there was rain before May. So this time domain may depend on the seasonality of your region of study. Okay. Then we did dot map. Small capital MAP is used to add layers to this interactive block here, right? Just close this. I'll show you differently what is block here. And if you use small map, this is a map function, and you create a function just like we created here. This is how you create a function in JavaScript. You pass parentheses and you return a value. This is the returned image. Image is returned with these bands added: NDVI, savvy, EVI, elevation. So you map this function, indices function. The name of the function is this indices. So what it will do, the small map function here, all the images in this surface reflectance data set, which is filtered, all images will be taken one by one and all the information will be added in all the images. All these extra 4 or 5 bands will be added. So effectively after this, what you will have, I'll just run this. Let's run this. So I don't know, we have much time. So yeah, so here you can see we have created a label also. These are the 5 different land use LULC classes for 2021 in this basin. In this, uh, I'll just show you the output and then we'll start backwards. It'll be pretty quick. I'll just remove layer 1. These are the image satellite images I printed. NDVI. Then we created an NDVI mask because we wanted our major classes. There was a lot of area which was devoid of vegetation there, or this thing, which is not a part of our study because there was a lot of snow also there. So we just created an NDVI mask. We calculated, we just checked all the NDVI, all the regions in the shape file with NDVI greater than 0.19 because Usually all these vegetation will have greater than 0.2. So different kind of vegetations we wanted to classify. So we just selected this particular. So we just updated the shapefile with this NDVI mask. So we know the only available region with us will be with the NDVI values greater than 0.2 approximately, right? So this is our LULC classification. This was our NDVI mask, and we use this NDVI mask over our shapefile. So you can verify which color shows which cover. From here, dark green is the forest, then purplish, or not very sure the color, but this is the urban, right? Magenta or something. Then light green is the grassland area here. Agriculture is shown in red, which will be in prominent regions here or near the rivers. You can see the agriculture activity. Then we have classified another class called barren, which shows some concrete material on the slopes. So this is how LULC map is created. But what went and what created this is, I'll go through this. So here you can see validation overall accuracy of 89%, which is this is the error matrix generated. So you can see forest, urban, agriculture, forest, urban, grassland, agriculture, and barren. Right, 0 is nothing because we started assigning classes from 1 to 5. So you can see this error matrix is generated after you classify the validation data set, okay, using your train classifier. We'll just have a look at the train classifier. So what train classifier did, it assigned 78 sample points to forest class, which is correct. One is forest. So it's like you can consider, if you just for a moment forget about this zero row here, just focus on this. So it's like 0, this is one forest has 78 points classified into forest, which is correct, but 2 points classified into urban, 2 sample points classified into grasslands, 1 into agriculture, and 0. So here we can see what is the confusion. So while classifying into forest, the 2 sample points were classified into urban and grasslands. So there is a very minute level of confusion here, which is okay. But seeing this that is the essence of this matrix. You can see the confusion in which classes you can see, you are getting, the classifier is getting confused. So if you go about in the third row, which is 2, that is urban. So you see 65 sample points classified into urban, but major 9 sample points are classified into agriculture. So however, it is pretty less compared to the accuracy, but you can see what is the confusion, right? As you can see, third is grassland. So grassland has 64 sample points classified into grasslands. So based on this only, we calculate the statistical indicators, overall accuracy, users accuracy, producers accuracy is calculated based on this. So ideally, all if we speak ideally, this matrix should be a diagonal matrix, right? From here it should be a diagonal matrix. All non-diagonal elements should be 0. That means that is 100% classified. So when classifier classifies perfectly, all the points for forest go to forest, all the points of urban goes to urban, all the points of grassland goes to grassland. So all the statistical indicators are based on are derived from this error matrix. That is the essence of this matrix, right? So we have seen the map and accuracy. Now we'll just go about how we train the classifier. So I have showed you that training data is into another script here which didn't load, so I'll show you after this. So we are using split factor of 0.8, right? But before that, what you do, using you have to create samples from your region using your classes. Collection properties is LC class, which I have assigned to all the training data classes, right? LC forest is 1, urban will be 2, 3, 4, 5. That is the value of LC for all these. Then the scale is the scale of your data set, land set, 30 meter you can give, whatever. If you are using Sentinel, you can give 20 meter, 10 meter, right? Then random columns. So it will create samples from here and it will assign a random column with random numbers, right? Then as it is a random, it will filter. We are using a split value of 0.8, right? So if you want, we can print this and visualize. So we are classifying training and testing. So we have to filter these samples dot filter less than random split. So if these samples, the number of samples which have values less than zero point 0.8 will be converted into training samples, and the samples which have value greater than zero point 0.8 will be converted into testing samples, right? So so basically you have to use this image. This image is the image which you want to classify into land use, land cover. So you have to clip region, you can select bands. Which are the bands? So these are the bands, prediction bands, B4, B5, B6, B7. Then these are the calculated indexes you added, NDVI, NDVI, SAVI, elevation slope. So you have to make a list of these bands, and these bands will be called as prediction bands. Prediction bands means these are the bands classifier will be using in the images, right, to get the different reflectance values and use them for classification to segregate pixels. So that is why this is important. If you remove NDVI from here, the NDVI values will be removed from the images. Like NDVI image band is added into the images, but classifier will not consider that NDVI band. So it will affect your accuracy again. So this is how you have splitted your data into training and testing. Okay, it's pretty simple. This code is also available on Google. You can go and check this, how it creates samples of your. This is the classes. Classes is your merged training data. Merge this training data points here, right? This, which we have already explained that it is coming from this script. So you have created samples also. Now what you do is you create samples. Just a moment, I will go back. Yeah, here you created samples here. Then you split it samples using, because here you are assigning a random column named random. Okay, so random column will have random values between 0 to 1. So zero point 0.8 shows 80%. So based on that, you have split into training and testing. So this training will be used for training the classifier. Okay, so how do you do that? You use something called, you create a variable classifier. You use EE stands for Earth Engine. Earth Engine dot function you have to call classifier. Dot classifier class will give you a classifier. You can use random forest, or you can use any other if you want, like smile control space. It will show you different smile car, smile gradient, naive Bayes, random forest, right? So usually random forest is pretty efficient, so you can use random forest and it used, what it does is it randomly creates samples from the data set, right? And based on that, it creates decision trees. So like you can pass the number of trees, like how much trees you want it to use for classification. So some value you can pass it, like around 1000 to 2000. Then you basically, the dot, you can see, often dot is there. This is called chaining in computer science. Like you are piling up functions onto the previously finished function. So once you call this random forest, then you pass again dot train. You now, this train function will have a list of parameters, right? Features, class property, input properties, bands. So these are the bands, prediction bands, which you have to pass. Class property is the which class, based on what class you want the classifier to do the training. So it is LC, which you have already assigned to all these training data points here. Features, training is your sample here, right? You split it, training. So training dot select. After that, you have to select all these bands. So these are the same bands actually as these prediction bands. So you're selecting, it's up to you. If you want, you can skip some of the bands from here. It totally depends on you and your study, which bands you want to select for your training. Okay. Now there is called validation testing dot classify. Yeah, so here it is this classifier, right? You have already created this classifier. I'm just going where it is classifying. Yeah, so here it is doing the classification. Image is our Landsat image, right? This is the image which we have updated with NDVI mask, selected bands, clipped. It is also filtered, right? I'll just for help here. This is this L8 image, right? We have done everything here, filtered it, then applied indexes also added in each band. In each image we added all the different bands and DVI indexes as bands we added. Then we did median, like it will give you a central image out of that. So this median function is basically an aggregate function. You can even use mean here depending on your study or mode you can study. So basically what it does is it creates a overall composite of your one image. Okay, so this L8 is being referred to as image here after being updated by NDVI mask here. So this particular image is being classified here. Dot select bands dot classifier. So dot image dot classify is a function. You have to pass this classifier here, but this is the classifier you have created and you have trained. So this classifier, any image will have a function dot classify image dot particular. You select the same bands, right? Dot classifier and classifier. So this variable will have your classified image. So that's why we added it to the map dot add layer class. Minimum value 1 to 5. Palette, these are the different colors we have given for different classes. So this color here will have a value 1, 2, 3, 4, 5. And this is the map you are seeing it here. This is the LULC map, right? So training the classifier, you got the classified image. First you trained this classifier, then you brought your image, then you did dot classify, you pass the classifier here, and this variable will have the classified image. After that, once you got the image, you know how to add an image to the map, right? Add, so any image, whether it is a classified image or first image of any data set you imported or any image you uploaded, you can add as a layer. You added a layer, you gave visualization parameters, you gave some name, you ran it, and it got added here. That is the story. So now there is you can calculate areas for each class in LULC image. So there is that code is also available easily in the Google Earth Engine. You can just, or Stack Overflow sites or discussion sites are there. You can go and you can check the areas available there for this programs available to calculate area. Okay, I'll just go through this. You can use reducer.sum function. So .sum is reduce region is a function used for different images in the Google Earth Engine. Reduce region is you want to reduce the pixel values based on some aggregation. This is reducer. This is your aggregate. Reduce.sum, group field 1, group name class, geometry region. Scale is 30. Maximum pixels is e to the power 10. You need not give max pixels, but in case you run out of any issues that you are trying to do some computation on an image on a certain scale, and it shows you that not enough pixels, like it exceeding pixels, you get an error of exceeding pixels in your console here, then you can probably give a max pixels. So if it gives you an error of like it cannot exceed 1 E9 pixels, you give 1 E10, so that your max pixels is more than that, so that you can avoid that error and it will help you, right? So basically this comes under optimizing the extraction of resources while you're working with the JavaScript code. So you can see here it will help you calculate the areas also. These are the areas in square kilometers. Forest 98 square kilometer, urban 47 square kilometer, 1873 square kilometers, right? So that is how. So what we did for this project, what we did was we did analysis for 2021. Then we did, like you can see scripts here, no? 2021 same LLC image we created for 2010 for 2090, and we just checked the differences between the different land use, land cover patterns. What was the growth and what was the area enhancements in forest for from 1990 to 2000, then what were the enhancements to 2010 from 2000, then what were the enhancements in 2021 from 2010. So that is a kind of study you can conduct using Google Earth Engine. Basically, this is a set position of panel. This is the code applied for this panel. So this also explains you how you can create apps. Like this is the widget here, right? You can see at the bottom here, LULC 2021. This widget was created using the programming code above. So you can even create widgets where you have even more interaction, selecting dates or all that. You can use code for that. So this is your supervised classification. I just wanted to show you the data, but let me try to load this data sets. This is the code for calculating the area. You have to just to pass immediate pixel area, add bands class from class. Yeah. So here we, after learning the basics of importing, filtering, and mapping, we just tried to do a supervised classification here. I couldn't show you the training data set. Let me try again. That you have to collect the training data sets using Google Earth Engine, because sometimes it's not possible. Sometimes if you want to do a study of a remote areas on Earth where you which is outside your nation or in some other country, you can use Google Earth Engine to create training data and conduct a supervised classification. And just after collecting training data, you can split into testing and training, then do the classified training using the training data set, create the classifier, and then you create your classified image, and then you use your validation. Okay, I have to show you how you calculate the accuracy, right? Accuracy. So it is this testing data set dot classifier you do. So this becomes your validation variable. So testing data dot classifier, you have to classify the testing data with the classifier again, right? Just like you classified your image here with the classifier. It's pretty simple. You classified your image here. Where is it? Where is it? Here, image dot select band dot classifier. You selected this image, classified using classifier. Same way, you just testing data you classify with classifier. You get this validation variable, and validation dot error matrix you do. LC is the class you have given, right, to the training dataset, and classification is the classification class it creates after classifying. The class by default classifier creates this. So using this, it creates test accuracy error matrix. So that's how you get this error matrix. I've printed this error matrix here so that it's visible here. That is why it's visible here. Then error matrix dot accuracy you do, you'll get the accuracy. So it's pretty simple. I'll show you a time lapse video also, which is a pretty interesting video posted in Google Earth Engine. So it gives you a historic timeline. Yeah, you can see here, right? So it's like a very broad idea of how geography evolved in terms of land cover. You can check. You can see here at the bottom from 1984 it's available. We should go to a better location. Uh, so we are moving towards Arunachal Pradesh. Yeah. So basically this is a time lapse video. If it's automatically running, it seems. Yeah, you can see the variations, right? It will start from 1984. You can see the years passing here. It's not loading properly, maybe. I'll just zoom out. Yeah. So you can check this out on Google, this time lapse, pretty interesting. And there are different kinds of study you can create using Google Earth Engine. You can create animation videos also out of this. All the help code will be available. Yes, it's not working properly in my machine, I guess. I just want to. Yeah, see, you can see visualize the shifts between the land covers. Should I increase or decrease the speed? Yeah, now maybe we should see. So this was, I think it's time. This was about the cloud platform which is there in public domain using uh, known as Google Earth Engine. So it's pretty useful these days because it combines both the satellite data sets or climatic data, atmospheric data, and it has all the programmatic approaches and functions available with which you can, with which it enables you to conduct a study worldwide, anywhere, sitting at your machine. I'll just close this for now. So that was all for today. I would like to close with this.